In this lesson, we're going to be doing two things. We're going to be talking about what happens if we reflect. We're going to be talking in this lesson about two different things. One is determining rotation angles if we reflect terminal arms. And there's some things about that that are important for other courses. It isn't necessarily about trigonometry. There's something in particular that students really struggle with that's embedded within that. And then what we're going to be looking at, and this is crucial to Math 30-1, is finding primary trigonometric ratios of what we call special angles in quadrant 1. And then we're going to extend that to quadrant 2 and 3 and 4 eventually. You still, after this lesson, will not really appreciate the idea of trig ratios, sine, cosine, and tangent, for angles that are outside quadrant 1. Everything we do will still be related, I guess, today to triangles, but tomorrow that changes. So to begin with, we're going to be looking at finding rotation angles from reflections. When a terminal arm of a rotation angle is reflected across an axis, the reference angle remains the same. This is crucial. For example, thank you. For example, if I have this rotation angle, or this, I shouldn't call this a rotation angle. I'm going to call it a terminal arm. So we're going to reflect that terminal arm, and I want to reflect it horizontally across this line. I think we know it's going to be going in this general direction. But just like when you look at your reflection in the mirror, if you are standing in front of a mirror and you're touching the mirror with your finger, your elbow appears behind the mirror and your body appears even further behind the mirror, but the tip of your finger is on the mirror. It doesn't move. It's what we call in mathematics invariant. That point that's on the mirror is called an invariant point. And for that reason, when I reflect this, and I have the advantage of being able to, I have the advantage of being able to flip it perfectly left-right. But when I do that, that point that was at the origin stays the same. So what we are looking at here, and I'm not going to use numbers yet, what we are looking at is for terminal arm number 1, what we are looking at is, that's theta. That's the rotation angle. For terminal arm number 2, this is the rotation angle. Correct? Always from the positive x-axis. Except that if I ask you, what is the reference angle? Theta reference for angle 2 and theta reference for angle 1 are the same. That's all this is saying. Okay, that's it. That's all it's saying. That the reference angles will be the same, it's just that it will be in a different quadrant. If I reflect a terminal arm from quadrant 1, I reflect it horizontally, it goes into quadrant 2. On the other hand, if I were to reflect this terminal arm vertically from quadrant 1, that would mean I'm going across the x-axis, which is kind of interesting. To reflect vertically, I go across the x-axis. This is a vertical reflection. The arrow was pointing kind of up. All right, so boy, that'll start your heart, eh? I've got two rotation angles up there. The terminal arm that lies in quadrant 1 has been reflected vertically across the x-axis. The vertical reflection happened across the x-axis. It happened across the horizontal axis. I have two rotation angles, but they have the same reference angle. If this angle in here is the reference angle for the first rotation, this is the reference angle for the second. They're the same numbers. This is the point of what's being said here. So we've got to pick up the pace just a little bit here because of that fire drill. I don't think I'm going to hand out rulers for this. Sketch a rotation angle of 38 degrees, write the reference angle. Is this your example? Okay. So I would say that looks about right. Just do your best to draw a straight line. If you're the kind of person that you want a straight line, use the edge of your calculator or something. And it's not really complete until we say this. Theta equals 38 degrees. The reference angle, however, is 38 degrees. The reason why I asked if this was your question is this is really so far a question from yesterday, isn't it? Okay. So that's it. A is pretty straightforward. B says reflect the original terminal line in the line y equals 0. So just a second here. What does that mean? Reflect this original terminal arm in the line y equals 0. Well, we know, everybody, this is going to be the point. We know the reference angle is going to be 38 degrees. The question is, which quadrant will it be in if I reflect the terminal arm? I don't want you to draw it again. If I reflect the terminal arm, which is here, don't draw that, in the line y equals 0. What does y equals 0 mean? And this is the thing that I said, Math 30 students get burned on an exam because of this. They mix up what y equals 0 is with what x equals 0 is. So who, after me instilling all kinds of confidence in you, who's willing to stick their neck out and tell me what y equals 0 means or what it is? It's the x-axis. So let me explain why this is y equals 0 first. Well, this would be y equals 1. This would be y equals 2. This would be the location where y is negative 1. This would be the location where y is negative 2. When you say y equals 0, you're saying the y coordinate is 0. What is the ordered pair for something like this? It might be 4, 0. X equals 4, y equals 0. What might the coordinate pair be here? Well, 2, 0. Every point on the x-axis is where y is 0. So that means we are reflecting something from quadrant 1. We are reflecting something from quadrant 1 across that line I've highlighted. This x-axis is y equals 0. So here's where it gets weird, and this is where you can psych yourself out. This will be a vertical reflection across the horizontal or x-axis whose equation is y equals 0. I don't think you can really get that out verbally or on paper without carefully thinking about it. The line y equals 0 is a horizontal or x-axis, but when we reflect across the horizontal or x-axis, it's a vertical reflection. Things that are above go below. All that means now, after all of that, is we can sketch in this terminal arm. We know I've established for you in our discussion before the fire drill that the reference angle stays the same. So if it was 38 degrees in quadrant 1 for a reference, it will be 38 degrees in quadrant 4. And now your job is to figure out what that rotation angle is. What we are doing right now are not things that I would ask you necessarily on exams. I'm trying to give you some skills that will be helpful later on in this course and later on in Math 30. So in order to find the rotation angle, I hope everybody is clear, you're going to take 360 and subtract 38. And I'm getting, you can double check my arithmetic here, 322 degrees. And I would say that if I told you you reflect a rotation angle of 38 degrees across the line y equals 0, what's the new rotation angle? I think you need a diagram to ensure you got this sorted out in your head. There's too many little things here that would pile up in your head and cause confusion. All right, let's try another one. What if we take that original terminal arm, which had a reference angle of 38, and we reflect it into a new quadrant? Well, the reference angle is still going to be 38 degrees. We've established that. I showed that to you, as I said, before the fire drill. Are you with us?
Yep.
Okay, just checking. So don't forget it was in quadrant 1. What is the line x equals 0? Well, it's this line. Because if I look over here, x is negative. If I look over here, x is positive. X is 0 right along the middle there on the vertical axis. So if I reflect now the terminal arm, which was in quadrant 1 with a reference angle of 38 across that line, it's going to be in quadrant 2. And the reference angle will be 38 degrees. That reference angle is going to be the same no matter how many times we reflect it, or where we reflect it to, as long as it's across axes. So now you have to figure out what the rotation angle is, and I would say to you that's child's play. 180 minus 38. How did I do there? Good? Thank you. Now comes the important part of this lesson, and this is a source of frustration for students. This what we're going to be learning. But to set your mind at ease, the reason why we're learning it here is because we know it's a source of frustration, and it's very important for 30-1. So if we see it now, and then we see it again later, and see it again in 30, then hopefully things will be okay. We're talking about trigonometric ratios of what we refer to as special angles. Special angles are any angles that are multiples of what we call a special angle. 30 degrees is a special angle. 60 degrees is a special angle. 45 degrees is a special angle. So all of those angles that I'm talking about, like 60, is a multiple of 30. 90 is a multiple of 45. 315 is a multiple of 45. 120 is a multiple of 30. It's also a multiple of 60. All of these locations here, and you have the angles labeled, they are all special. But I want to get your mind accustomed to working with these. All of these angles I've got up here are separated by 30 degrees. They're all separated by 30. So if you want to know what these locations correspond to, you can say, well, that's 30, that's 60, that's 90, that's 120. We just keep adding 30. And knowing how to get these angles for these positions is crucial. This would be 150, 180. All I'm doing is walking around the circle in a counterclockwise direction, adding 30 each time. Notice that when I do that, I hit all of the angles that are multiples of 60. 60, 120, 180, 240, 300, 360. All of these angles are multiples of 45. Now, it's also the case, you got it?
Yep.
It's also the case that 90 is also a multiple of 30, but that doesn't matter. These are multiples of 45, so this is 45. What's the next blue dot? 90. What's the next one? Add 45. 135. What's 135 plus 45? 180. And then you add and you add and you just go around the circle. So when you see, everybody, this diagram in the future that is not labeled, you need to be able to tell me relatively quickly what those rotation angles correspond to in terms of a rotation. So now, the most important exercise. You will see why I'm going to tell you this is important in a minute. But I'm telling you right now, if I have a 45, 45, 90 degree right triangle, and the hypotenuse is 2, you should be able to calculate the exact value of the other two sides. You need to know how to. If I tell you we have what's called a 30, 60, 90 degree triangle and the hypotenuse is 2, you should be able to tell me the exact values of the other sides. We need to know what they are to be successful in trig down the road. So how do we go about, I'm going to start with, actually going to start with this one. How do we go about finding those missing sides? Well, we recognize that since this is an isosceles triangle, it's isosceles because we have these two angles equal. What that means is that these two sides are equal. I'm not going to get into a geometry lesson here from junior high, but when you have a triangle with two equal angles and a third angle that's not, then it would be equilateral. If you have just two angles that are equal, then the sides corresponding to those angles are equal as well. What that means is if we want to find out the length of each of these sides, we can put an unknown variable here. And I'm going to choose to not use x and y. I'm going to use a. You can think of a as the answer to what those sides are. It's problematic using x and y because we're talking about the coordinate grid in many cases. So the Pythagorean theorem says the hypotenuse squared equals the leg squared plus the other leg squared, the sum of the squares of the smaller of the two of the three sides. So I square 2 and get 4. A squared plus a squared is like saying a pizza plus a pizza. You get 2 pizzas, so we get 2a squareds. I'm teaching you math along the way here today. This is not just directly about trigonometry, okay? I'm building those math skills. I divide both sides by 2 and I get a squared is equal to 2. I take the square root and I get a is equal to the square root of 2. Those of you in Physics 20 that we talk about plus or minus the square root, we're not interested in that here because it's a triangle. So what do we know? We know that those other two sides are the square root of 2. Okay, let's put them in the diagram. This is root 2. This is root 2. What about this one? Well, we play a little interesting game here, and you will get used to this ratio of the sides in a little while. That is going to be 1. And there is a reason why that side must be 1. It's the following. It's that if I take this triangle and reflect it horizontally and put it here and look at this whole triangle now. I'm focusing my attention on this whole triangle. That's an equilateral triangle. The reason is if this is 30, this is 30, and that makes this 60 degrees. This is clearly 60. This is obviously 60 because I've reflected it. So I have 60 degrees, 60 degrees, 60 degrees, which means it's equilateral. What does that mean? It means that this 2 is the length here, and it's also that length because it's equilateral. All the sides are equal. Since these two triangles are mirror images of each other, each of these bases must be 1 to add up to give 2. So we know in this triangle, and I'm going to go back to here and show the work here, we know that this is 1, so I can find the missing side. I'm going to call it B this time. I can write 2 squared equals 1 squared plus B squared. 2 squared is 4. 4 minus 1 squared is 3. B is the square root of 3. What is it you're doing on your calculator? Just put your calculator down. We're not using a calculator right now. So to begin with, thank you. To begin with, you need to know these triangles. They're called the special triangles. And when you get to math 30, we won't use the number 2 for the hypotenuse. We'll use the number 1, and that will cut the other dimensions in half. So if I said that this was 1, then this would be a half, and this would be a half of root 3, or root 3 over 2. And we'll do that next year. Okay, so you need to know those. You need to know these two triangles, or be able to figure them out. Because, we'll just watch me for a second. You need to know, be able to sort out fairly quickly by the time you get to 30, that the sine of 30 degrees is exactly, I don't know why I wrote 1/3, is exactly 1/2. Put your calculator in degree mode and take the sine of 30 degrees. Right? You need to know, everybody, that the cosine of 30 is exactly equal to the square root of 3 over 2. Exactly. If I take my calculator in degree mode, I am, and I take the cosine of 30 degrees, I get this number. But if I take the square root of 3, close brackets on the root, and divide by 2, I get that number. Now, you can sit there and go, why do I need to know? And if you're truly asking why, like why is it important? It's important because at higher levels of math, you need to know precise values. Okay? I know that's not a very satisfying answer. It's not, you need to know this because one day in your future, you're going to be out in the real world and you're going to have to know it. No, you're not. But you've decided to pursue this course in mathematics, which leads to 30-1, which leads potentially to calculus and engineering, and you need to know these things for higher levels of math. How do I know cos of 30 is root 3 over 2? Because I know this triangle. Well, I know this triangle and I've used it so much that I've memorized accidentally root 3 over 2. When I look at this 30-degree angle here, and I say cosine of an angle is adjacent over hypotenuse, it's root 3 over 2. Okay. So what your job is right now, I'm going to give you a minute to do so, is to write out all of these trig ratios by looking at the triangles. So tangent is opposite over adjacent. So you would look at your 30-degree angle in your special triangle and write opposite over adjacent. And again, I'm not asking you to write down what I've written down. I'm asking you to look at the triangles. That if you want to know what tangent of 30 degrees is, you look at this triangle that has 30 degrees in it, and you say tangent is opposite, which is 1, over adjacent, which is root 3. You need to know those primary trig ratios. And by the way, you're not given them in Math 20 on the formula sheet. You're given something else, and then that thing you're given in Math 20, you don't even see that in Math 30. So you need to know sine is opposite over hypotenuse, Cosine is adjacent over hypotenuse, and tangent is opposite over adjacent. So we've filled that in. Good. And I know that to many of you it's a why. What's the importance of this? Just trust me that it's important for higher levels math. Use your calculator to find the values of these. Now, if this were a Math 30 class, I would explain to you why this is the case. But you can follow along. I'm not going to do so. When you take your calculator, you can do it on your calculator, but I'm not. And you take the sine of 0 degrees, you will get 0. And when you take the cosine of 0, you will get 1. There's no triangle associated with this, and you don't quite understand why this is the case. That comes later. When you take the sine of 90 degrees, you get 1. When you take the cosine of 90 degrees, you get 0. This whole first page of this lesson is just dipping your toe into the trigonometric unit for 30-1. Okay? But to wade in a little further, and I don't know how this is going to go. We have one example, 2 examples left. There's no way we're going to get done because of the interruption with the fire alarm, fire drill. So well, we'll have to catch up the time elsewhere, but I'm not going to sacrifice things by rushing through here. I do want to just make sure we can do 4 first. Okay? Find the exact value of the side length x. Do you agree that this triangle, which I am going to highlight in green, is a right triangle, meaning we can use SOHCAHTOA? Okay. So x needs to be known, but the only thing you know in this triangle is this angle. Okay, let's just walk away from that for a second. I hope you would agree that this triangle I'm highlighting in blue is a right triangle. And from a Math 10 standpoint, you know one side and one angle, you ought to be able to determine this side in the blue triangle, right? But then that will be the hypotenuse of the green triangle, and you can then use trig to find x. So at first glance, everybody, you look at this, you go, well, it's a Math 10 problem. It's not, though, and here is why. When we say, I want to find, let's call this something. Let's call this A, or you could call it C. You know what? I changed my mind on that. I do not want to call it A because A might be thought of as adjacent, and it's the hypotenuse on one and the adjacent on the other. Let's call it C for the common side. It's a common side. So it's adjacent to the 45, and the 15 is the hypotenuse. So you would write cosine of 45 degrees, if this were a Math 10 class, equals the common side over 15. And this is what we're going to do here. It's not a Math 10 class. This is where you would be at in Math 10. But in Math 10, well, you would write this, C equals 15 times cosine of 45. And that's fine. That's true. But what you would do in Math 10 is you would do this. I don't want decimals. This is not an exact value. It turns out to be an irrational number. If I said, what is root 2 equal to? Root 2 is irrational. And you go root 2 on your calculator and say, oh, it's equal to 1.4. It's not. And I don't care how many decimals you read out from your calculator, that's not the exact value because they go on forever. So the difference is here, we're going to use our special triangles to find out the exact value of cosine of 45 degrees. So you would start drawing this, and I hope that after doing this a couple of times, you'll go, oh, right, I get root 2 here and here. I mean, you might have to call it A and then go from there. But that means cos of 45 is, looking at this 45-degree angle here, everybody, it's adjacent over hypotenuse. It's root 2 over 2. The exact value of that common side is 15 root 2 over 2. That's the exact value. And this is the difference, one of the differences maybe between dash 1 and dash 2. Dash 2, you'd find the decimal value and round it and say that's it. We want an exact value. Now what that means is that this, I can even put it up here. This is 15 root 2 over 2. So now let's focus our attention on the green triangle. The 60 degrees is what we look at to determine opposite, adjacent, and all of that. X in relation to the 60 degrees, I'll use yellow. This is opposite, and this is the hypotenuse. So now we say, well, sine of 60 degrees is equal to x over 15 root 2 over 2. And there are many ways that we could clean this up, but before we do, what is sine of 60? If it were math 10, you'd answer that by going, well, give me a second, and you'd go sine of 60. It's not math 10. You need to look at the 30, 60, 90-degree triangle and determine what sine of 60 is. So you would do this. Hopefully, you would remember, well, if I reflect that horizontally, that makes this 1, because I would get an equilateral triangle. And then you might even go, oh yeah, this is the one with the root 3. And it always will be. The 30-60 triangle will always have a root 3 in there. So what is sine of 60? Opposite, which is root 3, over hypotenuse, which is 2. So we can put in for sine of 60, root 3 over 2. This is equal to x over, it's equal to x over 15 root 2 over 2. There's so much you could do to solve this, but what I would suggest is that on the right-hand side, we're just looking at x over a number. If it were x over 5, you'd multiply both sides by 5 to get rid of it. In other words, I'm doing a bit of cross multiplication here. X will be equal to root 3 over 2 multiplied by 15 root 2 over 2. And we're multiplying a fraction by a fraction, so we can multiply across the top and we can multiply across the bottom. Across the top, this is unfortunate, and this is the only math course in high school where this happens. And we've thought about it. There's no way to get this course structured for students without running into a situation where I have to teach you something that you're going to learn later. Every other course, it flows so smoothly. But you will learn later that when you have the square root of 3 times the square root of 2, it is the square root of 6. If you want, you can confirm that on your calculator. You can take root 2 close brackets times root 3 close brackets, and then take the square root of 3. Now, they are irrational numbers, so I guess I'm not proving it to you, but I'm trying to convince you that it's the same. And then it's over 2 times 2, which is 4. This is the exact value of x. Let's just take a quick look at 5. Determine the value of this. Everybody figure out what cosine of 30 is. not on your calculator. Now, this is an interesting thing. When you go back to your calculator, look at mine. Do you remember when we did root 3 over 2 and we got 0.866? You can memorize accidentally that root 3 over 2 is 0.866. And if you go, well, let's see, cos of 30, it's root 3 over 2. That root 2 over 2, you might recognize it as 0.707 after a while. So if you want to know what sine of 45 is and you go, I can't remember. Oh, right, it's root 2 over 2. Every other number is like 0.5 or 1 or 2 or something like that. So this is root 3 over 2. This is root 2 over 2. We don't like numbers added to fractions. So we would most likely take this 1 and multiply the numerator and denominator by 2 to get a common denominator of 2. And then we could write 2 minus root 3 minus root 2. The thought of trying to catch up later really scares me. So I am not going to do example 3 today, and I'm not going to do example 3 later. And I'm not going to give you on your exam any questions directly related to that type of question. The questions you need to know how to do are on the next page, 3, 4, and 5. So on the next page, 3, 4, and 5 mirror examples 4 and 5 that we did here. Speaking as a Math 30-1 teacher, I know that that's the most important thing. The word problems, it doesn't matter. It's really not important. So 3, 4, and 5, give those a crack for tomorrow. I do understand I'm only giving you about 5 minutes, and I apologize for that. Sometimes that's the nature of this class.